Hey, what's up, YouTube? You know what they say, a LeetCode a day keeps the unemployment away. So let's get to it. For this problem, we're given a list of intervals, and we're told to insert a new interval and perform any operations necessary such that the new interval fits within the current intervals without overlapping. Let's start with the conceptual explanation. I've put together a visual that might help us conceptualize the problem. On the top, I've written the same example list of intervals that we were given in the problem. The intervals are spaced apart to represent the scale of each interval within the entire list for better visual reference. Our goal is to insert a given interval, in this case 2, 5, in a position where the starting points of the new and existing interval are in order. This implies that we need to iterate through the current list of intervals until we find a suitable existing interval for which this is true. Below, we have 4 possible cases which we can evaluate. Case 1 is 2, 5. Generally speaking, it's the case where the lower bound of the new interval can fall within the current interval, and the upper bound of the new interval lies outside of the current interval. So we begin iterating through the list of intervals and find an interval where the starting point of the new interval is larger than the starting point of the current interval. In this case, it's at I equals 0 or 1, 3. This means that we need to insert 2, 5 ahead of 1, 3. So if 1, 3 is at some ith index, then we need to insert 2, 5 at the I plus 1th index. Case 2 is 1, 2. Generally speaking, it's the case where both bounds of the new interval will fit within the current interval. We can apply the same operation as we did in case 1 to insert the new interval after the current interval. Case 3 is 0, 5. Generally speaking, it's the case where both bounds of the new interval fit outside of the current interval or between intervals. Since, for this case, the starting point of the new interval is less than the starting point of the current interval, we need to insert the new interval at the current index in order to bump the current interval ahead of the new interval. Hence the insertion at index I instead of I plus 1. Case 4, our last case, is 4, 5. It's the case where both bounds of the new interval lie completely above the current interval. But if you think about it, this case is actually the same as case 3 if we make our current interval 6, 9. So we are making the same insert call at I, but in this case I is 1 instead of 0. So with all our cases written down, we now see that the insert calls for cases 1 and 2 and 3 and 4 are the same respectively. For cases 1 and 2, we have the following logic. Just going to mark the same. So for cases 1 and 2, we have the following logic. And then for cases 3 and 4, we have the following logic. We can actually simplify this even more and remove this part. Because, of course, the starting point of the new array, new interval is less than the ending point of the current interval. The next step is to resolve any overlaps that the new inserted interval may have caused. I'm going to take the inserted list for case 1 as an example. Remember that for case 1, we inserted the new interval 2, 5 at the I plus 1th index. So this means that the current index is still I, which, to be exact, is still on 0. Let's just shift our focus towards intervals 1, 3, and 2, 5, because that's where the conflict is. First, we can see that 3 goes into 2, 5. Right? So 3 kind of goes into it. So what we can do here is update 3 to the upper bound of the interval that it crosses into. So precisely, we can update 3 to 5, since that's 5. So what we get is 1, 5, 2, 5. So at this point, we do not increment the index, I. So I is still here. So if we modify the current interval, we do not increment the index. And that makes our current interval 1, 5. So next, we can resolve the conflict that the current interval has with the next interval. In this case, we can see that we don't need the next interval at all. All right, so 1, 5, 2, 5. Both of these are 5s. So we don't even need this. So we can pop the I plus 1th interval off the list. So this really means that we have 2 cases, right? So if the current interval, so this case is if the current interval is completely above the next interval, or the ending number of the current interval is completely above the next interval. So what do we do here? We pop plus 1, and then do not increment I. Else if our current interval, if the upper bound of the current interval is greater than or equal to next, or the lower bound of the next interval, then we replace the upper bound of the current interval with the upper bound of the next interval. Do not increment I. Right, and then outside of all this, otherwise, increment. And so that is basically the second part. To resolve conflicts. Now that we understand the concept, let's start writing the code. I can first check if the intervals is already empty, and if it is, I just add the new interval and return the intervals. So at this point, I'm just going to make 2 variables called new start and new end, representing the lower and upper bounds of the new interval. Right. Next, we can check if the upper bound of the new interval is well, the upper bound of the next, we can check if the lower bound of the new interval is greater than the upper bound of the last interval in the list of intervals. And if it is, this means that all we need to do is append the new interval and return the list of intervals. So we get the last one, get the upper bound, and then if new start is greater than that, just intervals dot append new interval and then return intervals. So now we can start doing what we've been discussing. So I'm going to create a pointer, just I, and initialize that to 0. And I want to make sure step 1, find where to insert new interval based on starting point. So while I is less than intervals, I'll just say the current interval is intervals I. And then for start, for n, you'll for interval 0, 1. If cur start is less than new start, and new start end, then intervals, and we just insert the new interval to the I plus 1th index. And then break, since we found our proper location. So else if new start is less than current start, intervals dot insert I new interval. We just insert it to the ith position, therefore pushing the current interval right to the 1 to the right. And then break. And then for the while loop, we just have a I plus 1, and that's it. Now for step 2. Oops. We resolve overlaps that adding the new interval may have caused. So I actually don't need to initialize I to 0, right? Don't need. Because I is already at the position where we've inserted the new interval, either at I or I plus 1. So even if we have a while loop, we are still making a single pass through the list of intervals. All right. Since we need the next interval here, I'm gonna just do while I is less than length of intervals minus 1 per interval, right? Intervals I, and then next interval is I plus 1. Now if current interval I is greater than or equal to next interval 0, and current interval I is greater than or equal to next interval 1, right? So this is the case where the current interval is completely above, completely shadows the next interval. We'll stop pop. So what this means, well, if our current interval completely shadows the next interval, we don't even need the next interval. We just pop it out. And then make sure that I does not, that the pointer I does not get incremented. So we can decrement it, and then for the while loop, we increment it. Right? Then else, current interval 1, next interval 0. And this is the case if the current interval intersects into the next interval. I equals the next interval I, right? Just like we've said before, we've just set the upper bound of the current interval to the upper bound of the next interval. And then we just decrement I once to make sure that the pointer does not get a net increase of 1 for this iteration. -1 + 1, net 0. And then all we need to do here is return intervals. So let's run it. So we're missing something. elif. Intervals.pop. Yeah. Okay, so case 1 and case 2 are accepted. Let's submit. Okay, and it is accepted. And so this is the complete solution. So for the time and space complexity, the time complexity is O of n, because we are going through all intervals in the list of intervals. And then I'm going to define n as the number of intervals we have. And remember what I said earlier about there being 2 while loops, but we're not actually resetting I to 0 for the second while loop. So this is still a single pass, which means this is O of n time complexity. For space complexity, all we're storing really is the new interval, so it's O of 1. So that was it for LeetCode number 57. I hope you enjoyed the video. I'll see you in the next one.